So this is my third lab. We're going to go fast. We need to understand gravitation. Don't think about the Earth's surface, and also conservation of momentum. You also need to understand the difference between parallel and perpendicular components of force, as well as momentum, which you can see written out here because it's equivalent. And we're going to write out the actual specifics of momentum here too, which is going to be important in the coding process. Parallel components, they change the speed and the position. Perpendicular components, they change the orientation of the object, and they're going to be represented by p hat and n hat respectively. This project has two parts. The first part, we're going to find the mass of the black hole using a model, and the model is going to have perfectly spherical or circular star and black hole, and they're just going to be in space together, nothing else. And it's going to be the same. You're going to need to assume the same for the second part. And in this part, we're going to find the initial velocity of a spaceship just by trial and error, just plugging in numbers and seeing what happens. And you just want the spaceship to fly by the black hole, not crash into the star, not crash into the black hole, and escape the system. So here's the free body diagram. You can see this equal and opposite force of gravity between the black hole and the star. In the second one, it's a little bit more complicated. These equal and opposite forces, but there are three objects now, and they're all moving at different strange, confusing rates. Okay. We're also not going to be modeling these just because they make the program too complex, and the black hole is so massive that its acceleration is negligent. So for this model, we're going to need the seed, which is my email here, and the initial star mass. The initial velocity and position are going to be determined by that seed. The coded equations are essentially going to be that parallel and perpendicular force, momentum, etc. that we talked about. And we're going to need to rewrite the net force of gravity equation in order to find the black hole mass, which is going to be shown at different points in the process. So here's the process. I would show you, but it takes forever. So I'm just going to briefly show my code at the end of this to prove that I did it. But you can see here the net force at different locations. Well, no, I'm sorry, not at different locations. In general, the magnitude, the parallel, and the perpendicular. You can see the perpendicular is much greater, and that's why this is able to change the orientation so strongly. The mass of the black hole is also different because of rounding error in the program, so we need to find the average of these measurements. Again, elliptical, the gravitational force is greater when you're near the black hole. Parallel, speed change, perpendicular, direction change. There's some rounding errors. For this part, the second part, we have that mass from the first part. We have the planet mass, the spaceship mass, which are given, and you got these equations that are pretty standard. And then so you have the planet related and the spaceship related forces, the net forces, and then the positions relative to all of the different objects. So the initial velocity, I plugged in a bunch of numbers and I got this, and it gave me this beautiful slingshot around the black hole, which you can see in magenta, and you can see the planet orbiting the black hole in cyan with the black hole right here. It gets very close. In fact, it gets 268 meters away, which is not that much, or million meters away, which is not that much when you really think about it. And it's moving strongly to the left in the beginning, which you can see here, but a little bit up, that way it doesn't crash. I basically explain all that here. And then the spaceship takes advantage in that slingshot maneuver simply because of how close it can get to the black hole without actually falling in. Again, there's some error due to rounding. So what does that mean? Is the momentum different from the net force? No. Look at their definitions. What if the ship entered a new orbit, which I basically modeled essentially like the planet's orbit, roughly compared. Here is that initial velocity, which I plugged and chugged in order to get this orbit here. Here's it compared to the one from part one. You can see that the part one is much larger in overall magnitude, and then also it's going much stronger in the left direction. However, this one is also a little bit different in general, and that energy is essentially what's allowing it to maintain an orbit despite its small mass compared to the planet, which is really doing the same thing. So here is all of my different guys here. This guy is still finishing. Wow, I did it. And here is my code, my lovely, lovely, silly code here as well. You can see this unit vector here and the process repeated for the planet, for the ship, for their positions. And this is the same programming that's in here. It's just with a different starting velocities. So yeah.